There we go. Good morning, ladies and gentlemen, or afternoon, whenever you watch this, maybe 3 o'clock in the morning, who knows? So today we're going to talk about work and energy and how that can be related. So let's go ahead and pick a pen color. Now, work and energy do have a relationship, and we know that this energy relationship makes things equal in a broad sense. And as we go through this chapter and through some of the other chapters in next semester, we're going to realize that it's not exactly the case. So we're going to look at the work-energy relationship. So we're going to derive this and go ahead and take notes. We know that work is equal to force times distance. And usually when we say that work is equal to force times distance, this distance that's traveled usually starts at 0 and it travels so much so far. But if the object is moving and we apply a force on that object, that distance has now become the change in distance. So we slow it down, so the change in distance is actually smaller or larger. So we're looking at making this a little bit more sophisticated. And so the net work, after all the forces put together and all the changes we have, is that work is equal to F times delta X, change in distance. Remember this little thing, delta, means change. And then we also could say that since force is equal to mass times acceleration, now we have this as well. So mass times acceleration times the change in distance equals the work being applied. So continue on with this proof. So we're going to take a look at this equation for work. Mass equals the change in times the acceleration times the change in x. But for delta 2, we know from chapter 2, and that wasn't supposed to do that. So for chapter 2, we have this equation. The final velocity squared is equal to the initial velocity squared plus 2 times acceleration times distance times the change in x. A times change in x. A times change in x. So let's go ahead and manipulate the equation. Subtract both sides by vi squared. Move that over to the left. Divide by 2. And now we have this relationship. So we take this and put it into this equation where work is equal to mass times 1/2 times F squared minus Vi squared. And that's equal to work. Now this, in Vi 0, can be narrowed down to mass times V squared times 0.5, or 0.5 times m times V squared. This, my friends, is kinetic energy. So work is equal to change in kinetic energy. And this is called the work-energy theorem. And so this theorem can actually change kinetic energy into work and vice versa. And when you need to do this, you need to actually sum up all the net forces and to figure out net work in order to make this change in kinetic energy. So as we're looking at this, as we're looking into how this works, we're going to look at not only kinetic energy, but potential. Because potential energy is basically stored energy. And there's two types of stored energy. One is basically based on height, where the potential energy of an object above a surface is mass times acceleration of gravity times h. And this is what this scene you see at mgh, mass times acceleration of gravity times h. Now, I want to point out one thing. Mass is in kilograms, height is in meters, ag. is positive 9.81. Now, everybody's going to go, wait a minute, Dr. Bailey, didn't you say that in chapter 1 and 2 and 3, we're saying that acceleration of gravity is negative? Yes, that is true. But now we are definitely changing how we look and use the acceleration of gravity. And we're changing the perspective. We are looking at stored energy as we rise above the planet. And we're saying that the 0 point is ground. Now, if we think, and we're going to level everything at the 0 point, because we're not going to change. We're not going to go below 0. That will cause too many headaches. And you guys are not ready for that yet. But wherever the surface, we'll call that 0, so we're measuring the height up. Mass is positive always. And so if we say gravity is negative, that means we have a negative potential energy. And for a lot of physicists, that doesn't make sense. So we're going to change gravity to make it positive for anything dealing with energy. I hope that makes sense, and let me know if we need to rephrase this. Now, other sources of potential energy is what we call springs. The potential energy of a spring is 0.5 times kx squared, where k is a spring constant. The distance is basically when you pull or push this. So so if you push a spring in, you're actually giving it potential energy. Now the 0 point is where there's no force acting on it. So we have a spring, and say it's hanging down, and it looks like something like this. Usually the coils are pretty much equal. The distance between this and this point is usually, say, about, it may be a meter, maybe half a meter, whatever. This is the 0 point. So if we pull this way to stretch it out, the distance that we pulled is this from here to here. That's the distance we pulled, and when we do that, we're giving it potential energy. If we push it in to this point, this is x, this is the distance that we pushed it in. We're actually pushing in the spring, giving it potential energy. And this is what that means. 0.5 times k, a constant, times x squared. I want to take a look at this. I'm going to go through these couple of examples and let you know about how they solve these and just give you equations. Now remember, kinetic energy is 0.5 mv squared. So we've got two items. We got this and we have this. So we're saying that the kinetic energy of the bowling ball is equal to the kinetic energy of the tennis ball. So 0.5 times mass, this is mass of the bowling ball, times the velocity squared of the bowling ball. I use subscripts to figure out what object we're talking about. 0.5 times mass of the bowling ball, tennis ball, excuse me, and the velocity of the tennis ball, and that is squared. We want to know how fast this is. Look at this equation, those cancel. And so mass of the bowling ball times velocity of the bowling ball squared divided by mass of the tennis ball is equal to the square of the tennis ball. So if we take the square root of that and the square root of that, we should get the velocity of the tennis ball, and that's what we're looking for. I'm going to have you guys figure out how to solve the